Hello everyone. Today in this video I'll be discussing about a concept of 2D wire mesh or 2D basically 2D spring mesh instead of saying wire mesh. So this I have taken up a problem from Pathfinder that is challenge your understanding question number 3 from the chapter of surface tension. And the problem says that you have an elastic film which is modeled in form of a square grid bound by very small springs each of stiffness k, so that the potential energy of such film, if stretched by uniformly and isotropically, can be given by k into root s minus root s naught whole square, where s naught is the area of the unstretched film and s is the area of the stretched film. Okay, so first we have to basically derive the first relation, that is u is equals to k into root s minus root s naught whole square. Now there are two methods to do it. First method is basically spring division. Suppose I'm making this wire mesh look basically spring mesh look like something like this. Okay. Now consider any two squares. Suppose I'm considering these two squares. Okay. Can I write these squares equivalent to like this? K by 2, K by 2, and other two are K by 2 also. Now why I am writing k by 2? Because the adjacent square will have another spring of k by 2 which will add up to give a spring of constant k. We know that parallel combination of spring gives addition, and series gives the harmonic kind of inverse summation whole inverse, right? So the same thing we are doing here, that is basically we are dividing the springs equally. Now what will happen that each square, how many squares are there? The number of squares will be L square by A square, where A is the length of one spring and L is the relaxed length of the whole square mesh. These are the number of springs. And now what will be the change in potential energy? Delta U will be half K by 2 into root L root A plus delta L A, which is the stressed length, minus root A whole square. Or I can write it as a dash root a dash minus root a whole square, where a dash square whole square is equals to the final area, right? Hope you get it. So this is the change in potential energy of one spring of one such square. Now how many springs are there in one such square? It is 4. Just multiply by 4. Now you will get k into root a dash minus root a whole square. So this is the basically change in potential energy of one square. Now total change will be L square by A square, right? Into now n, basically that is into n, right? Just a minute. Sorry, it will be A root A dash minus root A, where A is the length. I am not taking A dash to be the area. A is basically the length. Now n is L square by A square. So you can say that the final change will be K L a dash by a minus L whole square. Now L can be written as minus root s naught. Now what is L a dash by a? L a dash by a is nothing but root s. I am explaining why. Suppose this is my square and this is side length a. It changed to a dash. Okay, it has increased to a dash. So the L will change proportionally by root L into a dash by a. So area will be S will be L a dash by a whole square, right? Because it's a square mesh. Hence L a dash by a will be root s. Similarly, L square is equal to S naught. L will be root S naught. This is the expression of final potential energy, right? Hope you get it. So this is my first method, that is by spring division. Second method is will be taking such lattice. Like if we consider this lattice, this is one unit, which is of k. Second will be something like this. Third will be something like this. Fourth will be something like this. Basically, we are making such division. The division is such that it will be perfect. So in this kind of lattice or unit cell, you can say, in this kind of unit, the total spring is 2 which is equal to 2 into k by 2 a dash minus a whole square. Sorry. In this case also on further evaluation you'll get delta u is equals to k root s minus root s naught whole square, and that's the answer that matches with this one. So first question is done. Second question says that we need to find the excess pressure or the pressure dependency inside the balloon on its radius r. Assume vacuum outside the balloon. So what is the work done? Suppose we'll be using virtual work method. I used the method. I used the word term work done before only. Apologize. So suppose this is radius r and it expands by some dr. So what will be the work done? dw will be p into 4 pi r square dr, right? Now what will be delta u? Delta u will be k into root s minus root s naught whole square, which can be written as now you can write du to be k into 2 into root s minus root s naught by 2 root s into ds, which you can say it to be k into 1 minus root s naught by s into what is ds? ds can be written as 4 pi r square dr. Now s naught by s can be written as k into 1 minus root 1 minus r naught by r, which is equal to 4 pi r square dr. So the final expression which we will get is basically in 1 minute. There's some issues. Yeah, here the ds will be 8 pi r dr. Yeah, it will be 8 pi r dr because s is equals to 4 pi r square. ds will be 8 pi r dr. You can say it like this. Now cancelling one r and further evaluation, you'll get p to be cancelling dr and 8 pi r all those. You'll get p to be 2k into r minus r naught by r square, and that's the final answer. You might be wondering what is the relation with surface tension in this problem. Now you know that any suppose you have some amount of small drop, it may try to it may tend or try to minimize its surface area, right? You have very small thickness, then what will happen? It will just approach a very small figure, which is basically a sphere. We know that. Now, in this case, in case of surface tension, we write that U to be K times S or gamma times S, where gamma is the surface tension. Same concept is applied here. Here, the in this case of spring mesh, if you think S not tends 0, you can write d delta U or U only, which is Ks. Now, for a spring mesh of negligible length, you can write U to be Ks, where S is the area and K is the spring constant. Basically, this formula is almost consistent with the surface tension mode. In surface tension, we write gamma S or gamma A, but in spring, we write Ks or Ka. Similarly, in case of surface tension, we derive that inside a spherical drop, the excess pressure delta P is written as 2K by R. Now, in this case, it's 2K into R minus R naught by R square. Well, there must be some reason, right? So you can understand it why we are saying, because if R not tends 0, then it will be 2k by R. We know that this spring mesh, the balloon has only one layer, and in case of drop there are two layers. In case of one layer, that is 2k by R or 2p by R. So basically the formula is almost consistent with the surface tension one. A very important thing to note here is that 2D spring mesh is like a spherical drop, or you can say 2D wire mesh is like, what can I say, like a bubble or a soap film. You can say like it's a soap film with only one surface. Unlike in soap film there are two surfaces, it has only one surface. Hope you enjoyed it. You can also search for some problems. I'll be posting one today in the community post. You can try that out. Hope you enjoyed it. Thank you and have a nice day.